Welcome, this is a NXL FP1 video. This is on the final part of complex numbers, the complex number chapter. And in this video we're going to be looking at quartic equations and how to find their roots. Now, quartic equations, you may go, okay, well, what does a quartic equation look like? Generally, the most familiar will be the standard x graph, the x squared graph, and the x cubed graph. Should be fairly familiar to most of you, but the quartic is a little bit different. Now, obviously, it's got four. You can have it in a number of ways, just like when we talked about the cubic and the quadratic in terms of real and imaginary numbers. Okay, so obviously, when we've got something like this, or you may have a quartic equation where you've just got ax to the power 4. So when the number in front of the x to the power 4 is greater than 0, you may have 4 real roots, and when the number in front of the quartic number in front of the x to the power 4 is greater than 0, we get this W shape, and it might look something like this. Okay, so that has 4 real roots, and what we mean by that is, basically, we know this is the x-axis and this is the y-axis. We said a real number is any number that you can think of. And obviously, this crosses the x-axis at some point. It might be 1.22, we don't know. All we know is it's actually a number that you can say. Basically, it's not root minus 1. So therefore, we know it has 4 roots. Similarly, so that is where a1 is greater than 0. So a1 being a1 is the number in front of x to the power 4. However, when a1 is less than 0, okay, we get this sort of M shape. Okay, so excuse my rather crude drawing again. Where it looks like a distorted M. Okay, so we still get 4 real roots. It still crosses the 4 x's, just kind of inverted sort of thing. Basically, it's just reflected. It's the upside down of the. Basically, it's just a standard reflection in the x-axis. So, as I said, it's just like when we said a1 is less than 0 and a1 is greater than 0, or vice versa. All we're doing, we're f of x, and then we're doing the f of minus f of x. Okay, so that's all it really is, these two graphs. Now, this may not be the only quartic that you do. So you may have a quartic that does this. So where it doesn't have 4 real roots, it might only have 2 real roots. It might have something like this, where basically you've got 2 points of intersection along the x-axis. You've got 2 real roots and 2 imaginary roots, and them 2 imaginary roots can only become in the form of a complex conjugate pair. Because when you have an imaginary root, it has to be. That's the only way at further pure 1 level that we imagine them to be. So basically, when you've got a complex root or a complex number as a root of an equation, then it must have a complex conjugate pair as roots. Now, quartic. Well, the only things I can think of is 2x squareds, or 2 quartics. Sorry, 2 quadratic graphs. So basically, what we're saying is this x to the power 4 is something like this. So it could factorise something like this. a1x squared plus b1x plus c1, and that is times by a2x squared plus b2x plus c2. Okay, so basically what we're saying is, obviously, when you this a1 business, by the way, that's just the number. That's the first number in front of the squared, and this a2 is another number that is in front of an x squared. So basically 2 quadratics we've got there. And if you were to times them out, you would get, we could get this, depending on what the values of a, b and c are. Okay, so what we're saying is this really factorises into 2 quadratics. Now, we said quadratics can factorise or they can't. Well, that's true, they all factorise. But some of them factorise with negative numbers. So basically, some of them factorise to give what we now know as a complex conjugate pair in further pure 1. So both of them do factorise. No matter what quadratic you have, they all factorise. Just some give imaginary roots and some don't. Okay, so therefore, taking that into account, so these are the number of ways that this can factorise. Now we said it's made of two quadratics essentially, that's why we've got that W shape as two quadratics put together essentially. So that's what it kind of should look like really. But if one of them factorises, then we may have a situation where is x take a number, I'm going to call this alpha. So x take alpha, so remember alpha is just a number, x take beta, beta is just a number, and then we may have a quadratic. So basically one of the quadratics may factorise and one may not. Or we could have a situation where they all factorise, so both quadratics factorise. So we have they always have 4 factors. So don't get wrong that these do factorise. As I said, it's just like we learned it in the quadratic equation of complex numbers. They all factorise, just the ones that look like they don't factorise, where they give a negative square root kind of thing, we said they have a complex conjugate pair. I mean, obviously you know that because you've watched the other videos, or you just know that anyway. Sorry. So basically, you get the idea. We could have 4 factors. So it's x take alpha beta, x take gamma and x. So therefore, we could have either one of these 3 situations. Obviously, that could be the other way around. But basically, this is essentially what it could look like. This is what it should look like, and then we can factor it to one of these 2. Okay, so we can either simplify 2. So this essentially is made up of 2 quadratics. So I mean, this is just a given quadratic and a cubic, quartic. This is just a given quartic that I'm going to work through with you in a minute. And we say it will factorise to this. That is a given. Because it is a quartic will factorise to a quadratic. That's just because our law of indices say that because when we have to times 2 out, then the highest power we get when we times an x squared by an x squared is x to the power 4. So and there's no other way that we could times an x cubed by an x, but so yeah, so actually that's a good point. So this could factorise into a quartic. So this quartic could factorise into a cubic and a quadratic, or it could factorise into 2 quadratics, and then therefore that could factorise into one of these 2. Okay. All right. So there's numbers of ways that this can factorise. Sorry, I really can't contradict myself. So it can end up being a quartic. So this quartic can end up being a cubic and a single factor, so just x plus 2 for example, or it could be factorised into 2 quadratics, and then they would factorise to something like this. Okay, so sorry for I almost contradicted myself by saying it can only factorise to 2 quadratics, so sorry, I'm getting ahead of myself there. But essentially for FP1 you will really only see as 2 quadratics. You might see as a cubic, but that's a little bit nasty. Okay, so that's just to summarise. You can either factor into a cubic and a linear function, so x plus 2, or it can factorise into 2 quadratics. That's what a quartic can end up being. So the key question is, how do we get to these stages? I mean, how do we get to this stage for a kickoff? Now, let's go through that quartic that I've got on the board there for you. Okay, so I mean, obviously we can't tell straight away by looking at it, going, okay, well is that going to factorise into 2 quadratics, a cubic and a linear function, or can we not do anything with it at all? Well, obviously we can do something with it, because otherwise I wouldn't have it on the board. But generally, of all the questions that I've seen, they will say this is a factor, or they will ask you to prove something is a factor. Or, if they don't do that, then you could just start from 0, put 0 in, and if you get 0, but obviously you won't. So basically, if they tell you a factor, then you can work through that, and they'll go through a method for that. But if they don't give you a factor, because this should equal 0, and what we're essentially trying to do is find values for x, where this quartic equals 0, you could just, if they don't give you a factor, if they don't say x plus 4 is a factor, the factor will be something very easy. So it'll be x take 1 is a factor, for example. Then you'd put f of 1 in and see what you get, f of 2 in and see what you get, f of 3 in, etc. You might go on. And you could go the other way, so you could do f of 1, see what you get for that. F of minus 1, see what you get for that. Now, they won't go, if that is the case, basically, if they don't give you a factor, then you could just trial and error kind of error thing, where you try to find what factor is. Now, it's a key thing to remember from Core 2, f2, if that equals 0, I'm not saying it does for this equation, it doesn't. If f2 equals 0, remember, x is not, x plus 2 is not a factor. Because if x plus 2 was a factor, then x would equal minus 2, and that's clearly not what is the case. So therefore, it's easy to remember when you get f of 2 equals, when you put 2 in, and if that came to be 0, you've got to remember the factor is x take 2. Because if x take 2 equals 0, therefore x equals 2, and that's what you've subbed in. Okay. Alright, so that's just a key thing to familiarise yourself from Core 2. This is actually this topic is actually quite heavily based on stuff that you will have done in Core 2. So if you've done Core 2 yet, as I said, I'm not sure if you're picking this up at A2 level or if you're just doing it through your first year. So if you haven't done Core 2, this will be the way I'm going to work through. Oh, I've rubbed off the Quartic, that's fucking brilliant. Right, one sec. There it is, sorry. So what I'm going to do now, when I write the Quartic back on the board, is I'm going to be using something called the factor theorem and remainder theorem. Now, if you don't know what that is, the reason I'm saying it now is if you don't have a clue what I'm talking about when I talk about the factor theorem or the remainder theorem, which is kind of what I just a little bit went through then, please do check out my EdXL Core 2 video on factor and remainder theorem. I give a bit more detail in the C2 specification. But from this moment on, I'm assuming you know what I mean by factor and remainder theorem. And I'll explain why we use it in a minute. Okay, so the equation I had on the board, the Quartic I had, for God's sake, you know, I would need to buy some more pens. You'd think I wouldn't with the amount I've got, but I'm going to have to use some old pens I've had for ages in a minute. Okay, so I had this Quartic on the board, x to the power 4, take 2x cubed plus 21x squared, and take 8x plus 68 equals 0. Now, I'm going to give you a bit of a heads up on what factor and remainder theorem is if you're not quite sure with it, but if you're completely unfamiliar, as I said, please do check out the video. Okay, so this is could be a typical question in an exam. Well, it's not typical, actually the exam questions are quite different from the actual topic questions, but this is a general kind of fundamental topic question you might get that is in a workbook, for example. So we're given this Quartic and we say the question says find all factors of this equation, or it might say simplify this as or solve the equation. Okay, we're given that the first point actually of the question that's in my book, it says show that x squared plus 4 is a factor of this equation. So we know it's a factor. Okay, so I'm going to go through why it is and how that helps us. Okay, so we know x squared plus 4 is a factor. Now you can't do x plus 4 equals 0, so therefore x squared is 4 and x equals the square root of 4, and you can do plus or minus 2, sub it into the equation and get an answer. I wouldn't do that because we need to prove it is a factor. Now when something, linking, the only thing that we can think of, well actually, I think it's probably better explaining like this. Okay, so I'm going to rewrite out the equation again. So Quartic x to the power 4, take 2x cubed plus 21x squared, take 8x plus 68. Now I'm not going to put that equal to 0 because what we've got is, this is a factor, and what we mean by a factor, when we're talking about factors, say a factor of 6 is, could be 3 or could be 2. Basically it's something that is times by something else to give the answer. That makes any sense. It's basic maths. I'm probably making it way too complicated. Basically what I'm saying is we times this x squared plus 4 by something to get this x, to this Quartic equation. Now, going back to what I said before, if you times two quadratics together, it will get you a quartic. Now that is obviously a quadratic. Just when you factorise that quadratic, it gave you the x is cancelled out. So that's x squared plus 0x plus 4. That is a quadratic, but they just missed out the 0x because obviously there isn't any x's, so they didn't include it. Now, I said two quadratics make a cubic because you times x squared by x squared. As that is a quadratic, then the other factor must also be a quadratic. Now we don't know if this other quadratic factorises or not, but I'm just going to assume it doesn't. Well, obviously it does. As I said, all quadratics factorise. Some just have imaginary roots. But I'm just going to write this other factor because it's a quadratic times a quadratic. So I'm just going to write the other factor as a quadratic. So let's go ahead and do that. So that's a1 x squared plus b1x plus c. Okay, so that's what it will look like. Basically what we're saying is this quartic equals this x squared plus 4 quadratic times another quadratic that we've got to find out. Okay, actually, yeah, so I've kind of skipped ahead of myself on this question a little bit, actually, to be honest. The first question said, okay, prove x squared plus 4 is a factor. Okay, so I've kind of jumped ahead of myself to another part of the question. So as I said, that's what it will look like when it is factorised. Okay, but we need to prove this x squared plus 4 is a factor. Now, anything that is related to factors that you know about is factor and remainder theorem, which is kind of why I explained it. Now, if you think of what factor and remainder theorem says, if something is a factor of something else, so basically if x squared plus 4 is a factor of this quartic, then when we use the factor and remainder theorem, basically when we divide it by, when we divide the quartic by the quadratic, we will get an answer of 0. But obviously the quotient bit is this other factor that we're looking for. Because the quotient times the answer, because we're dividing the quartic by the quadratic, when we divide that by something else, that will give us what we need to times this quadratic by to get the quartic, because it's a factor, it just gives us another factor. So as I said, if you don't get that, please do check out my factor and remainder theorem video, but I'll probably do a better job of explaining it in that video actually. So, basically what we're saying is, if we divide this well, it doesn't equal 0 actually, that's the wrong way of saying it. So if we divide this this quadratic by this quartic, we should get no remainder. It should go into it perfectly because it's a factor, it's times by it. That's a better way of explaining it, actually. Think of it that way. And it will give us an answer and it will have no remainder. Okay, so it will be, if you divided 8 by 2, you won't get 3.21 because obviously it's not right. You would get 4. Hopefully, if you could do some maths. So what we're saying is, when we divide the quartic by the quadratic, we should get 0 remainder. Okay, so that's what we do. Now, the factor theorem, remainder theorem, basically just dividing it. And I've kind of summed it up there. Actually, probably did that better in my other video. Anyway, just proves then people that aren't paying attention actually get rewarded. Anyway, so just go ahead and do the factor and remainder theorem on this. Actually, that's way too big. One sec, I've just drawn that far too big. Okay, so, one sec. Try this again. Do apologise, but it gives me some branding business awareness in my back, which obviously is, you know, completely irrelevant to maths, but, and I'm not being paid for that, by the way. Anyway, okay. Right, so just using the factor and remainder theorem on this quartic. So if this is a factor, then it should equal 0. And this quotient should give us the other factor. Okay, so the first thing we're going to do is divide this x to the power 4 over x squared, and that will give us what we need to times by the x squared plus 4 to take away from this quartic. As I said, factor and remainder theorem, basically I'm just assuming you know this. Sorry about that, I just had to change the lid on my pen. Well, not lid, change the pen. Anyway, so what we were saying is we need to divide this x to the power 4 over x squared, which obviously gives us x squared, times x squared plus 4 by x squared, and take it away from our current answer. So, obviously that's the first term in the quadratic. So x squared, and then it's x squared, so it's x to the power 4 plus 4x. Now, we've not got any x cubed, so to stop any confusion, I'll just write 0x cubed. plus 4x squared, take 0x plus 0. Okay, then we continue this idea, so it's x squared plus 4, and then you divide it by whatever the answers of this, so obviously the x, the quartic part cancel, and then 2x cubed is left, and then this obviously gets us plus 17x squared, take 8x plus 68. Okay, do the same again, so minus 2x cubed over x squared, which obviously gets us take 2x, which is what you write over here. Okay, times this by negative 2x, which gets us negative 2x cubed, take 8x, plus, because we've not got any x squared here, so it's plus 0x, and then it's 4 times negative 2x, which is negative 8x, plus 0. Now, you don't have to write these 0x and 0, but I just put it in there. Oh, sorry. Just had a bit of a thing there. So anyway, you take away the negative 2x cubed, which obviously adds it, so that gets rid of the x cubed. Then we're just left with 17x squared. And then the 8x is cancelled, and then we just 17x squared plus 68. And if this is truly a factor, then we should get rid of both parts now. So 17x squared over x squared is just plus 17, so it's x squared plus 2x plus, sorry, x squared take 2x plus 17 as a final kind of answer. So 17 times x squared, obviously 17x squared, and 17 times 4 is 68, so obviously when we take them two away we are left with 0 as a remainder, so therefore it is a factor. What we're left with here is this is a factor, this x squared plus 4, but this quotient is also a factor. Which is this ax squared plus bx plus c business. Okay, so assuming you've got through that, what I'm going to do is I'm going to quickly rub this factor business out with this factor theorem, and hopefully you understand why it equals 0. Okay, so just quickly go ahead and rub that out. So as I said, hopefully you've got that down and see where I've cut it from. Okay, so we said this quotient is x squared plus x squared take 2x plus 17. So if that is, as I said, basically what we've done is x squared, the quartic divided by the quadratic, and that obviously gets us something else we need to change this quadratic by to get this quartic. So we rewrite this out as a pair of two factors, okay? I think my camera's flashing me, so 1 second, just plug my camera in. So what I've done, so just put my camera on charge, but I've kind of wrote it out in, rubbed off all the other random bits of information that were dotted across the board here, and written it out as a pair of factors. Okay, so this is what it looks like so far. Now if you remember back to that other stage, as I said, all quadratics factorise. Just some of them give roots which contain imaginary numbers that give a complex root, or complex conjugate pair. Now, this, just by looking at it, x squared take 2x plus 17, is clearly not going to factorise. So the only way we can find out, well, it's not, it does factorise as I said, but it's not one that we can clearly just depict out of our minds with, you know, x plus 5 and x take 2, for example. It's not as simple as that. So the only way we can get around this problem is by using the quadratic formula. So that's exactly what we're going to do. Now, obviously, well, not obvious actually, but it looks kind of obvious that this equation is going to have a negative square. It's going to involve some kind of, I'm going to start from my head, imaginary numbers. That's the whole point of this topic. Okay, so you put some space to one side. Okay, well, x squared take 2x plus 17. Just sub it into the quadratic formula, so you get negative b, which is positive 2, plus or minus the square root of b squared, which is 4, take 4 times 1 times 17, brackets, over 2a, which is just over 2, remember that equals x, and work out what this 4 times 1 times 17 is. Sorry, I do apologise, just had a bit of a recent cold, so, but obviously you can't catch it through technology, so, you know, you're pretty fortunate. So 4 times 1 times 17, that gets you 68, so it's the square root of 4 take 68, which is obviously negative root 64. So if we take this on, therefore, see, negative root 64 is root negative 1 times root 64, which is, we know root 64 is 8, and root minus 1 is I, so it's 8i. So therefore x is equal to 2 plus or minus 8i over 2. Okay, so therefore x is equal to 1 plus or minus 4i. Okay, now we know that is x equal to, so therefore when we put it, remember when we said we put it in this kind of factor form? So if we write the x squared plus 4 business over here, and this x take, and then in brackets 1 plus 4i. Okay, so all we're doing is putting this in the quadratic thing. So it's x take 1 take 4i. Okay, so that's what it looks like in complete factorised form. Now you could factorise this x squared plus 4 into, well, might be quite difficult actually. If you can think of the top of your head what x squared plus 4 factorises to, please do let me know, otherwise I'm just assuming I'm being a complete idiot and can't factorise a simple quadratic. In essence, that way you get to, and if you could factorise x squared plus 4, you would continue with that, but because I'm a bit of a numpty and it's too late and I need to go to bed, even though it's only whatever, I don't know, 8 o'clock, well, just tired, long day. Anyway, so as I said, you just factorise that if you could, and say you might not even be able to, it might be alright actually, I might not be losing my head just yet. Okay, so that's one question that you might get. Another question kind of focuses on this complex conjugate root thing I did. Okay, which is actually quite a nice one. So what I'm going to do is I'm going to put the question in front of you. Well, no, you know, obviously, hopefully you've got your computer or whatever in front of you. So technically, kind of am putting it in front of you, but anyway, waffling on. Okay, so as I said, hopefully you get that and you can copy that down. So I'll just give you a second to, if you do want to copy that down, you can do. Okay, so I'm assuming you've copied that down. Right, so this other question that I've got on the board, that I'm going to put on the board, okay, so we're given this quartic equation, so 2x to the 4, take 3x cubed, take 39x squared, plus 120x, take 50 equals 0. We're told that 3 plus I is a root. We're not asked to show that, we just told that 3 plus I is a root of this quartic, obviously. Now, there's a couple of key elements in here. Obviously, you're going to end up using a factor theorem at some stage. Another key bit of information you need for this question is that, obviously, 3 plus I is a root of a quadratic, because obviously we've got quartic made up two quadratics, or a linear and a cubic, but obviously that is part of a quadratic root, so therefore, as we said, the roots of a quadratic are complex conjugate pairs. I don't want to give too much away, obviously I've given quite a lot away there, but anyway, just a bit of a head start. So that'd be the question you might get in the exam, so I'll just give you a minute or two to pause that and have a go at that question, if you can actually see it on the board, if the focus is in. It might have been completely out this whole video. Anyway, so I'll just give you a second if you want to pause the video now and have a quick go at that question. I'm going to go through the answer in 8 minutes. Well, I say minutes, probably going to be more like a second or two. Okay, so just let you pause the video. Alright, so hopefully you've had a go. Okay, so as I said, complex conjugate pairs. Now, a complex conjugate pair is just a complex number and another number which is just the same complex number, but we change the sign in front of the imaginary part. So therefore, if 3 plus I is a root there, we change the sign in front of the imaginary thing, so therefore 3 take I is also a root. Okay, so if we know them two are roots, we know they are roots of a quadratic equation. Okay, so obviously if we put this equal to some kind of other form, okay, like we did before, so if we follow the same principle that we did before, now you might not have done this. Okay, you might have skipped a step, but I'm just going to go through the full thing. Plus 120x take 50. So just rewrite out the equation, and we said that's equal to 2 quadratics. Okay, so the first quadratic might be ax squared plus bx plus c. A and b and c are just numbers. And we know 3 plus I is a root and 3 take I is a root. Now when we said before in the previous part of this video, I said when you get 3 plus I is a root, therefore x take in, so brackets x take 3 take I, close brackets, that equals 0, and that is a root. Okay, so that's what it looked like in a quadratic function that is factorised. So therefore the other root must be 3x take in brackets 3 plus I, double close brackets if you want, that also equals 0. So therefore, we rub the zeros actually, because these two, to understand this we need to go back to our quadratic video in the complex series for the pure one. Okay, so we said this is equal to a quadratic and another quadratic. Now we can just put the roots in and we can use the standard theory of how we get a quadratic from complex roots in that we did in another video for the pure one. So what I'm going to do is I'm just write the roots first. So we're going to almost go backwards in terms of what we're doing in this video. Okay, so just write the roots in. So it's x take brackets 3 take I, and x take brackets 3 plus I, close brackets. Okay, so what we actually want to do is, in other videos, we've factorised this and got it into something like this. But to do that, to work out what this other unknown quadratic is, we need to do the same kind of thing we did before, where we basically divide the quartic by the known quadratic we have to find the unknown quadratic, because we said a quadratic times another quadratic is a quartic. So therefore we know one quadratic and we don't know the other one. We want to know this other one, and we've got the quartic. Okay, so I'm trying to break it down. So that's why we're essentially dividing the quartic by the quadratic. That's essentially what the factor remainder theorem says. It's just dividing one function by another, but you just call it the factor theorem because when you have when you divide a function by its factor, you will not get anything overall. You will not get a remainder. You will get an answer by like 6 times or something, but you won't get any remainder. So obviously when you divide it, you should get 0 sort of thing. If that makes any sense. As I said, if it doesn't, please do check out my factor theorem remainder video. But I'm just trying to keep ahead in case them people haven't yet figured out they need to watch the other video. But I'm assuming you are. Anyway, so going back to our video that we did about quadratics involving complex roots. To find the original quadratic, we just expand the roots. We've kind of already put it in there. So what I'm going to do is I'm going to ignore this question for the moment, so we can expand this quadratic that we know the 2 roots of in order to help us find this other unknown quadratic. If that makes any sense, I'm probably not explaining it very well at all. Okay, so as I said, the 2 roots are x take 3 take I and x take 3 plus I. So just expand this these 2 factors out. So as I said, you can either times these 2 together or these 2. They are the same thing. So I'll just write it again. Actually, I did try without writing it, but you know I'll probably make a mess of it. X take 3 plus I. Okay, so it's just a case of expanding it like you would any other quadratic. Okay, so you do the x squared first, that's generally what I do, so it's x squared, and then you times negative brackets 3 take I times negative 3 brackets 3 plus I, so you're going to get as a positive because negative times negative, so that's plus, and then you just do the double bracket, so plus 3 take I times 3 plus I. Now you might want to put them in square brackets, like I'm going to, but you might not want to either. And then it's negative brackets 3 take I times x, so it's just take x brackets 3 plus 3 take I. Do the same for the other one, so then for it's negative x times, so it's negative 3 plus I, negative brackets 3 plus I times the x, which obviously gets you negative x brackets 3 plus I. Okay, next line is just a case of expanding this, so obviously the x squared doesn't do anything. 3 times 3, that's obviously plus 9. Okay, negative 3i, negative 3 times, 3 times negative I, negative 3i. Now I'm not going to write that because, well, I am actually. So it's take 3i, but you're also going to have plus 3i. And then we've got negative I times I. Now, bearing in mind, what we've got there is negative I squared. Okay, I'll just write that in actually. So negative I squared. Now, I'm just going to explain something. So you know, I is root negative 1, so therefore root negative 1 is, times root negative 1 is minus 1, sorry. And we're taking away minus 1, so we just add 1, but I'll write that in a minute. Just expand the next part, so it's negative x times 3, so it's negative 3x. And then it's negative x times I, which obviously gets you plus xi. And then you do the same for the next bit, so it's negative 3x take xi. Okay, so it's just a case of simplifying this down, cancelling terms. Obviously, we've not got any other x squared, so it's just x squared. Look for the x's, so we've got on here, we've got negative 3x, negative 3x, so that's obviously negative 6x. Okay, now I'm just going to rub out at this stage. So what we need to now is the real, so basically, we look at the imaginary parts, now they should all cancel. So negative 3i plus 3i, obviously that cancels, as we expect. And the plus xi cancels with the negative xi, so all the imaginary parts so far have been cancelled. However, this negative I squared, now we say negative I squared is take away minus 1, so obviously you'd write plus 1. Okay, so therefore we've got plus 9 plus 1, and then that is all we've got so far. So it's x squared takes 6x plus 10. Okay. So that's our quadratic that comes from this. Now, if you wanted to double check your working, which I'm definitely going to do now before I continue, what we've done is just expanded these two factors to give us this quadratic. So really, this quadratic that we've come up with should factorise to give 3 plus I as a root and 3 take I as a root. So if you wanted to double check you calculated the right quadratic, now I might not recommend you do this straight away if you're a bit under pressure in your exam in terms of time, but it's a nice thing to go back and check at the end of your exam to make sure you've done it correctly. So, you know, just a bit of advice there. So what we're doing is negative b, which is plus 6. So it's 6 plus the square root of b squared take 4ac, so it's just square root of 36 take 4 times 1 times 10, which obviously gets you negative, this is probably, you can't use a calculator obviously, I don't know why I attempted it, so it's plus 6 plus or minus the square root of minus 4, which is obviously plus or minus 4i, because obviously that's going to be, sorry, one sec, it's not 4i, is it? Because it's negative 4, so it's negative, it's root negative 1 times root 4, which obviously 2i, sorry, 4i, over 2a, which is just 2. So therefore that equals x, so therefore x is equal to 3 plus or minus I, which is what we've got as root. So we know that is the correct quadratic for our answer, but that's just a bit of proof checking really, and you know, hopefully you're assuming that I'm right. Just wanted to prove to you, obviously myself as well, but obviously I knew I was right. Okay, so we know that's a quadratic, so what we can do is we can, instead of writing these two separate factors, we could write these two factors as one quadratic. So what I'm going to do is, because I'm running out a little bit of space, I'm just going to rub these two factors out and rewrite it as a quadratic. Okay, so it's x squared take 6s plus 10, and that gives root of 3 plus I and 3 take I, which is just what I had written before. But I've just rewrote it, so they give myself a bit more room. And they could have just rubbed it all out, but... So I'm hoping you got that. I'm just going to rub that out again. Okay, because obviously we're going to be using a bit of the factor theorem. Okay, so hopefully you got that. I've talked through it, so you should understand it anyway. Okay, well, I say should. Sometimes I don't get what I'm talking about, so got to help you. So now we know a quadratic, we know the quartic. We need to know what we times the basically we've got an unknown quadratic times a known quadratic gives us a quartic. So therefore we just divide this quartic by this known quadratic to give us the unknown quadratic. Or you could say we use the factor theorem to find out this other factor. I think my way sounds a hell of a lot simpler, but it's probably less mathematical in terms of my actual words. But that's why I'm here to talk through some questions. Okay, so it's just a case of using your factor theorem or dividing, whatever. So we put the big number under the square root, so it's 2x to the power 4, take 3x cubed, take 39x squared plus 120x, take 50, and we're dividing our known quadratic of x squared, take 6x plus 10. Okay, so it's just like any other factor theorem / remainder theorem question that we've attempted before. So as I said, hopefully you've got it right so far. Okay, so it's just 2x to the power 4 over x squared, and we times the answer by x squared by this quadratic, and then we take it away from our answer, from our quartic, okay? So 2x squared over x squared obviously gets us 2x squared. We times 2x squared by the quadratic, so 2x squared times x squared gets us 2x4, which obviously should cancel with a 2x4, because that's why I'm doing this method. Cancelling each of the first times and maybe some of the others, so it'd end up being 0. As I said, hopefully it should be 0. It should be if this is a factor. 2x squared times negative 6x, that gets us negative 12x cubed. Yep. And then 2x squared times 10x. Sorry, 2x squared times 10. That's obviously plus 20x squared. And then we haven't got any x's to deal with, so it's just plus 0x plus 0. Okay, and we're taking all of that away from our quartic. Obviously that's not going to cancel to be 0, so we have to draw another line of working. So that x squared, take 6x plus 10, square root of the answer. Or divide by the answer, whatever. It's not really square root, so I keep saying that. So the 2x to the power 4 cancel. Obviously negative 3x cubed, take away negative 12x cubed. Obviously that's going to add 12x cubed. So obviously that's plus 9x cubed. Okay. So negative 39x squared, take away positive 20x squared. So that's obviously negative 59x squared. And then it's just the rest stays the same because we've not taken anything away. So it's plus 120x take 50. Okay, so it's 9x cubed over x squared, which obviously just gets us plus 9x. So that's the next part of this quotient. Okay, so we times the quadratic by 9x and take it away from what we've got as an answer now, which is our cubic, because that's what we're currently up to. Okay, so 9x times x squared obviously gets us 9x cubed, as expected. 9x times negative 6, so that should give us, sorry, just want to not going insane, so that should give us negative 54x squared, and then 9x times 10, because it's plus 90x, and we haven't got any single numbers, so it's just plus 0. Okay, we're taking that all away from our cubic. Obviously that isn't going to cancel, so therefore we have to draw another line of working. X squared takes 6x plus 10, divide by our answer, because we keep dividing it till we get 0, or as many as we can do. So the 9x cubed cancel, and then it's negative 59x squared, take away negative 54x squared, so obviously adding 54x squared, which obviously leaves us with negative 5x squared. 120x take positive 90x, which is just plus 30x. And we can't do anything with the 50, so it's just take 50. Okay? We did the same method of negative 5x squared over x squared, which gets us negative 5, or take away 5, and we add that to our quotient. Now, by the looks of our quotient, this says, obviously we can't have x to the minus 1 of anything, so this should be the end of our answer. So we timed the quadratic by negative 5, so that the first answer is negative 5x squared. Negative 5 times negative 6x gets us plus 30x, so it's looking good so far. And our negative 5 times 10 is negative 50, which you can see when we take that away from the answer, clearly it gives us an answer of a remainder of 0. So these are our two factors now, this quadratic and this quotient quadratic. So we've got two quadratics. Okay, actually you didn't need to rewrite that as a quadratic, to be fair. You know, in our original one I said change the roots to the actual quadratic. We're only going to be converting it back, but I just wanted to show you how we're working through this question. As I said, you know, you can completely ignore what I'm saying. But then begs the question why you're watching the video. Okay, so what I'm going to do is rewrite this quartic in terms of its new two roots. Okay, so we know the two quadratics that make up this quartic, that times together, are the quotient and what we're dividing it by. Because we know what they divide it by gives us a remainder of 0. So obviously, there is a factor, and we times that by 2x squared plus 9x take 5 to equal this quartic that we've got. So it's x squared take 6x plus 10 bracket times 2x squared plus 9x take 5. Sorry. Okay, so you could factorise if you were to put it into. Now I don't. Hopefully, I don't need to go through factorising them two for you. But I would personally just avoid going straight into trying to factorise it yourself. Well, it's up to you actually. Well, this obviously the first quadratic here that we worked out by that we were given the roots obviously doesn't factorise. We know that, so we could just rewrite it as the roots that we were given before, which is x take 3 plus I and x take 3 take I. Okay, and then this other quadratic that we've come up as the quotient in our factor and remainder theorem part of the question, that's 2x squared plus 9x take 5. Now that looks quite complicated. I can't think of that off the top of my head. Well, it's going to factorise too, but it's always going to be 2x and then x. So just to make sure I'm not going insane and it's actually really easy to factorise, I'm not just being lazy, which I suspect is the case. Yeah, so it's 2x take 1 and then x plus 5. Okay, so there are our factors. As I said, you could have used the quadratic factorising formula to work out this quotient quadratic, which is what we times our known quadratic by, which we worked out by using the roots and working backwards sort of thing. Okay, so that's a summary. They're the two types of questions you're likely to get. So you're either likely to be given an imaginary part, imaginary function, sorry, not imaginary function, a complex conjugate pair or a complex number, and so that's a root of the quartic, and you could obviously just done what we've done here, realise obviously when we have a complex root, then obviously it comes in a complex conjugate pair for a quartic. Work out the quadratic that's associated with, as we've done here, as we did before, sorry, and then just divide the quartic by our known quadratic to find our unknown quadratic, because we said two quadratics, when you times a quadratic by a quadratic you get a quartic. Now obviously, so you could have a cubic and a linear function, so an x cubed and an x, but you could always, if you're going to do that, then you could always simplify that cubic to a quadratic and times all of it by a linear function, which would give you two quadratics if you follow my method. But if not, just it's always going to factor two quadratics. But you might get a cube. Anyway, waffling on. Don't need to know all that. So essentially, what I'm saying is, if you're given a complex number as a root, then they must be a complex conjugate pair. Find what that quadratic is, divide it by the quartic, gives you the unknown quadratic, which you can factorise. If it does factorise, which it should, it'd be quite hard for you to get a quartic which has all four of its roots as complex numbers, or two complex conjugate pairs. Okay. But you might also get what we had at the start of this video, where I was talking about x squared plus 4 was a factor of something, and that's already a quadratic, so we just go straight into dividing it using the factor theorem to work out this other quadratic, which you factorise using the formula. Okay, so that's a summary of complex conjugates with quartic equations. And that is the end of complex numbers. So what I'm going to do in my next video for complex numbers, because obviously I'm assuming you've finished complex numbers now, I think I'll probably make a couple of videos. So I'll go through some past paper, because I've got a booklet from Physics and Maths Tutor. It's a good website, and there's a solution banks on there. I've just pulled the NXL FP1 worksheet, which is just basically, it's got all the exam questions that have ever been asked on complex conjugates or complex numbers, and I'm going to go through a few of them. As I said, if there's any in particular that are to do with complex conjugates that aren't currently on my YouTube channel, please do let me know, and I will either try and talk you through them in the comments section or produce a video if that doesn't work. I don't think I'll be doing, as I said, I'll be doing FP1 past paper videos as soon as I upload all the topic videos first. So anyway, thanks for watching, and we'll see you in the next video, or whatever you decide to watch. Anyway, thanks for watching, we'll see you in the next video.